Hello everybody, welcome back to another installment, Damage Control Assistant Senior Enlisted Curriculum. This is going to be Chapter 5, Lesson 3. I'm Lieutenant Timothy Mueller, and today we'll be talking about the free communication effect on vessels. So now let's start off by defining what free communication is. Free communication is, just like free surface effect, free communication is a virtual rise in the center of gravity that comes from damage that we take and an influx of water from the ocean around us. This virtual rise in the center of gravity, just like free surface effect, is measured in feet. Now, we look here. Think about the free surface effect, but now we have an influx of water. If we look to the diagram on the left of the screen, let's say we have a ship originally steaming right here with the waterline at waterline knot. Then something happens. We hit a mine, take on damage, hit some rocks, whatever it might be. Now, this compartment, which I've drawn here, is now open to the ocean, which means that water can flow in and out however it pleases. Now, if we had just the free surface effect, so pretend that we had all this water rush in and then that hole was magically closed off, we remember from the free surface effect video that as we incline, that surface is just going to incline right along some little pivot point along its original waterline. However, when we have free communication effect, this whole allowing water to flow in and out, we don't have just that. As we incline from waterline 0 to waterline 1, we actually have an influx of water because we know that in order to equalize pressure, the waterline on the inside of the ship that's open to the ocean has to be right at the same level as the waterline that's outside of the ship. So as we incline to waterline 1, instead of just having this small waterline CD, we actually have this waterline here at AB. So we have an addition of weight horizontal on the ship. How is this horizontal weight affecting the center of gravity in general? Well, if we think back to what we've already learned, we know that adding weight somewhere causes that center of gravity to move towards that weight addition. But if we remove weight, it causes the center of gravity to move away from that weight removal. So here, as the ship inclines, we are constantly adding and removing weight. This waterline here keeps going up and down. However, this waterline on the outside behaves. That means at every single angle, there's going to be different cosine corrections that we would have to do to take care of the movement of the physical center of gravity of G. Now, like the free surface effect, is there any way that we can make this a little bit easier, just instead of having constant corrections for different angles, just have one thing that we can model for many different angles? There is, and it's the free communication effect. It is applicable just at small angles, just like we have with the free surface effect. And like I mentioned before, it too is a virtual rise in the center of gravity. Now let's look at these points here. Like I said, just like free surface effect, it causes a virtual rise in the ship's G. So it's going to go from G naught to this GV. We see that the free communication effect, that influx of water, is causing horizontal movements of G, but there's constant horizontal movements depending on the angle of inclination. By rising to a virtual center of gravity, it takes care of all possible angles of inclination within a certain range. Now I'm going to jump to the bottom of this list here and say that the free communication effect and the actual effects that it has on the center of gravity, it takes a lot of approximation to actually get a formula that's easy to use and that we can apply to a situation readily, very quickly. So keep that in mind in the next video for when we actually derive this free communication effect equation. Now let's move to probably the most important bullet of all of this. So in order to have free communication effect, and we're going to go into the formula here in a few seconds, in order to have free communication effect, we must have all three of the following conditions. We have to have flooding water, center of gravity is off the center line. So we see here, this compartment here has a center, the flooding water always has a center of gravity right along here, right along the middle of the compartment. If this compartment spanned the entire beam of the ship, so if we went all the way from starboard to port, then it would have a center of gravity that'd be along the center line. That's not free communication effect, and we're going to see that applied in the formula here in a second. So first, the flooding water has to be off center line. Next, the compartment has to be partially flooded. Why does it have to be partially flooded? So that it allows the influx of water. If this was all the way solidly full, so let's say we had a compartment that was right here. So it's just this compartment here. And this is full of water. It's always below the waterline. Then there's no water rushing in and out. That means that there's no constant moving of that horizontal, the horizontal movement of the center of gravity, which means we don't need to bring a virtual center of gravity into the mix. So we have to have a partial flooding, or if you want to say, there has to be a free surface inside of that compartment in order for us to have free communication effect. Then the third one, the compartment has to be open to the sea. It is possible for us to have flooding water off center line and a compartment partially flooded. Let's just say we had a fire main rupture. A fire main rupture on, let's say, a berthing area all the way to the starboard side is off center line, and it's also partially flooded. If we only have 1 feet of flooding water on deck, that's partially flooded. However, we have to be open to the sea. It has to allow influx and outflux of water through this hole, this damage that we incurred. Now that we've gotten the requirements for free communication effect out of the way, here's the formula for it. So FCE, free communication effect, and that's measured in feet, linear length, just like free surface effect, equals B times L times Y squared divided by specific volume of the liquid that's coming into the tank times the final displacement. We've already seen B in the free surface effect. That is the width of the flooding. L, we've already seen as well. That's the longitudinal length. So that would be the length, if we had this perspective, out of the board or into the board in that direction. The new term that we have is this Y, and it's Y squared. So it has the highest exponent in the term, so that means it's the most important. So we better find out exactly what it means. So Y is the distance from the center line to the compartment's center of gravity. When you come to DK school, you're only going to be dealing with rectangular compartments. So all you have to do is find the center of gravity of that rectangular compartment and then take that distance from the center line. That's going to be your Y. So in this diagram that we have here, the center of gravity of all this water is always going to fall right along this line. So if we know that, our Y would be this distance right here, going from the center line to where the center of gravity is. It's the horizontal distance from center line to the center of gravity. Then in the denominator, we see two terms, and we've already seen them before. We have specific volume, and this is the specific volume of that flooding water, which is going to be typically salt water, so 35 cubic feet per long ton. Then we also have final displacement, and that's the final displacement of the ship plus all of its flooding water. Now, we think about free communication effect and free surface effect. I mentioned that one of the requirements that we have for free communication effect is that it has to be partially flooded, so it has to have a free surface. That does not mean that the free communication effect also has free surface effect in it. We have to add the combined effect of them both to find the total virtual rise in center of gravity. So the total virtual rise due to damage that we take on equals free surface effect plus free communication effect. If we want to have a total virtual rise in the ship's center of gravity, so everything that contributes to virtual rise, we think that there's tanks on board, and the tanks are always partially full. We never have a tank that's completely 100% full. We have to have it right around 95% to allow for expansion of oil or whatever might be in there. And it's never really at 0%. There's always going to be 1 or 2% because your low suction isn't perfectly all the way down. So we always have some sort of shallow or deep pocketing. You add all of those free surface effects up from the tanks, plus any free surface from damage or flooding, plus any free communication effect from damage. That's going to be our total virtual rise in the center of gravity. So the ship itself will have a physical center of gravity, and then it'll also have a virtual rise due to all these free surface effects and all the free communication effects. Now let's take a look at that formula again. We have free communication effect equals B times L times Y squared divided by specific volume times final displacement. The biggest term in there, the most influential, just where we saw with the free communication, or sorry, the free surface effect, was that B cubed. So the width of the compartment was the most influential. Now with this, we have that Y squared. So Y being the horizontal distance from the center line to the center of gravity of the compartment itself, that is the most influential term. If we double Y, so if we have a compartment twice as far away from the center line, then we increase the effect of the free communication by 4. If we have that Y, so if that center of gravity moves in, if it gets cut in half, then we reduce the free communication effect by a factor of 1/4. Now let's move into an example problem here. In this prompt, we are on a vessel, and we hit some rocks and we tear a compartment open. This compartment has a length of 20 feet, it has a width of 18 feet, and it has an overall height of 10 feet. And it's flooded all the way to it's flooded up to 4 feet. The compartment is on the port side, and the interior bulkhead is 4 feet from the center line. What is TVR, or total virtual rise? Now, we're not given anything about free surface of tanks, so we don't have to really care about it. All we care about is this added free surface effect and the added free communication effect, if we have free communication effect. Remember, we have to have all 3 of those limitations in order to have it. So we got to check for that, then we have to apply it. So first off, and also our ship originally displaces 2,100 long tons. So first off, we take on damage. We've flooded. We have to find out how much weight we've added to the ship so we can find our final displacement. Originally, we drew 2,100 long tons. We brought on length times width times depth. The compartment is 10 feet high, but it's only flooded to 4 feet. Divided by the specific volume of seawater, 35 cubic feet per long ton, and we get 41.14 long tons. Adding this to our original displacement gives us a final displacement of 2,141.14 long tons. Now, we know B, right here, width, breadth, the same thing. We know L, those are 2 things that we need for both free surface and free communication effect. We know specific volume, that's 35, and we know the final displacement. What's the only term we're missing? That term is Y. That's that distance from the center line of the ship to the center of gravity. And it doesn't matter if it's port or starboard. There's no positive or negative in that regard. The orientation doesn't matter. It's just the absolute value of the distance from the center line to that center of gravity of the tank, or the flooding compartment. So on this diagram, I've kind of scrubbed it down a little bit. We have to take the information that we've been given in the prompt and find out what our horizontal distance is. So we know that we've torn open this compartment, and it has an interior bulkhead 4 feet from the center line. So we know that it's open to the ocean. So and it's also on the port side. So it has to be right around here. It has to start and end right around there. And if we assume it's a rectangular compartment, length times width times some height, so it's a box, it has to go just like this. All right, now we're getting somewhere. We know that the center of gravity is going to be right in the middle of all that flooding water. If we know that the compartment is 18 feet wide, so if this is 18, we remember from our center of gravity and center of buoyancy lessons back in chapter 0 that the center of gravity is going to be in the centroid of a fluid, and for a rectangle, the center of gravity is just right in the half of that width. So this distance here from the center of gravity to this interior bulkhead is 9 feet. Now, that isn't all that we need. Well, we don't have everything on this diagram right now to figure out what our y is. We have to go back to our prompt and see if there's any more information that we can use. We know the compartment is on the port side. All right, we got that. But the interior bulkhead is 4 feet from the center line, which means that this measurement right here, this is 4 feet. Now, y is the distance from the center line to that center of gravity, which means center line, 4 feet to the bulkhead, then 9 feet to the center of gravity, meaning that this distance here, our y, equals 13 feet. Now we have all the information we need to solve our problem. We've already established that we have all the terms that we need for our free surface effect and our free communication effect. We're trying to find the total virtual rise, and I mentioned earlier in this video, the total virtual rise is going to be the free surface of our tanks, which we're going to assume is 0 because we weren't given anything in the prompt, plus the free surface effect, plus the free communication effect. So we got to pick one, start with that, then calculate the other, and then add them together. Let's start with the free surface effect. Free surface effect is just going to be L times B cubed divided by 12 times, in this case, 35, because we have seawater flooding in, times final displacement. And we're going to get an answer of 0.13 feet. That means that the center of gravity of the ship overall is going to rise due to free surface effect only 0.13 feet. Now for free communication effect, we have B, we have L, we have Y being 13, then we have 35 for the specific volume, and we also have final displacement. Plugging all those into the equation, we get free communication effect equals 0.81 feet. And that, just like free surface effect, is a virtual rise in the ship's overall center of gravity. Now we have our FS tanks, which is 0. We have our free surface effect, which was 0.13 feet. Then we have free communication effect, which is 0.81. Now we just add them all together. And we're going to get a final answer, which is going to be our total virtual rise in the center of gravity of 0.94 feet. When you come here to Damage Control Assistant School, very rarely will you be given Y up front for a free communication effect problem. You will almost always be given some condition about the compartment itself, usually the interior bulkhead. Sometimes you'll have bulkheads that actually go across the center line of the ship. So in that case, we would have, let's say, another compartment down here. We would have a compartment that would go like this. If you're given that the interior bulkhead is 3 feet, let's say, on the other side of the center line, so this is 3 feet, and the total width of the compartment is, let's say, 20 feet, you know that the center of gravity is going to be in the half breadth, so it's going to be at 10 feet in the middle of the compartment. But you also know that it's 3 feet over from the center line. So if all of this is 20, center of gravity is right here, this is 10, then 10 minus 3 is 7. That would be our Y, the distance from the center line to the center of gravity of that flooding water. So be careful in your prompts when you come to the school how you're given the information in each scenario. Is the compartment all the way across the center line? Does it not cross the center line? We'll also see something like this when we talk about trim. You'll be given the compartment number, which means you're given the forward bulkhead, and you're also given the length of the compartment. So from there, you can find the center of gravity. It's just going to be right in the middle of that compartment, and then you can find your moments from there. But that's going to be for another chapter. So right now, we've covered the free surface effect, and we've also covered the free communication effect. This pretty much sums up the virtual rise that we're going to see for ships that are steaming underway. There is another condition that causes a virtual rise, that's grounding and dry docking, and we'll get into that in future videos. However, I'm going to conclude this lesson with, I'm Lieutenant Timothy Mueller, and I hope you have a great day.